Welcome everyone for Cloud Computing and Big Data, our lecture 4 today on virtualization and data center design. So this lecture is a little bit a more conceptual lecture to understand the basics of a data center, which is really derived by virtualization techniques. And as I said earlier in the course, it's a bit out of sync because this should be happening way earlier. While you already had, of course, with lecture 2, 3, and so on, and the practical lecture 3.1 most notably, a more practical idea how you do machine learning in the clouds using HD Insight and MS Azure. The idea is, of course, getting to you the assignment 1 very early. So now we hopefully also will understand this lecture 4 then now today. What is actually now the basics of this data center design? So how you can go and create different virtualized resources. That in the end is also the backbone of this Spark cluster you have seen already in the previous lectures. Although it is very hidden from you. You use a Jupyter notebook. Everything is very nice. Python, you use a PySpark kernel. You use a Yarn scheduler. But of course, in the background, there's lots of things happening. And most of the things you will see there is fueled by virtualization. It's a basic technique in computer science. It's not even directly, let's say, only data center oriented. So basically 101 computer science and distributed systems and other courses in this university should also teach you about this. And I think they do partly. Hence, our introduction today to virtualization will be not so deep. We just give a couple of examples, what type of hypervisors are there, how they relate to hardware, and so on. We much more take notably, of course, a look on the data center design, which brings you scalability, which enables parallel computing. And of course, today would be also a little bit more into the idea of multi-tenant, multi-user. These are terms which we didn't touch upon so much, but think about that the data center is not just for you as a user. One, use HD Insight and you're done. Of course, this is really loaded, enabling scalability for a lot of different users doing different workloads, different applications on a daily basis. And we will look how this is realized using virtualized resources. But before we go into the material of this lecture, let us review what we learned the last time. Then in practical lecture 3.1, which was a practical lecture, as the name suggests. So we looked at a really interesting binary classification problem, which was, in the end, if you looked closely on it, not really binary, because we had this Chicago food inspection of restaurants, and then we learned actually much more classes to the problem, right? So we asked the question, are there really 2 classes, or can we join several classes? And if you remember, one of the classes that is basically joined with a PAAS is also a PAAS with condition. So in the end, both paths, those with PAAS and PAAS with condition, but you can also see that for us, for the prediction is at least something we maybe can combine. And this is inherent in many machine learning problems. So before you ever go towards a machine learning algorithm, you have to see what the data is, data understanding, data inspection, data visualization if needed, right? Infer the schema, maybe even the dots in a space, so you don't know. But that's machine learning, looking first what the data, and you cannot just throw a machine learning algorithm on it. That was one of the takeaway messages of lecture 3.1. Hence, we had to look at the data a little bit more and understand that there is a Chicago data set of this, failed and passed labeled set that gives us the idea of why we have to each of these different axes here, which are the, complaints about a restaurant. Oops, which are the complaints about a restaurant here. No, somehow the cursor doesn't work today. No idea why. Now it works. So you have this Chicago restaurant, but it has always a guiding label. Is it pass or fail, or as we said, 5 classes. But then we learned also, luckily, we have 2 data sets available, a training set and a test set. We use the training set, don't care about the test set in the beginning. And this is an important part. Also, when you think about our larger idea, and this is really the central, you hopefully learned from the course last time, the idea of how the building blocks of machine learning somehow relate to each other, things we know and things we don't know, and we don't maybe need to know, but still something which, you basically can derive for almost all machine learning problems. Here, it's a very much supervised learning setup. In unsupervised learning, you don't have a guiding label. So also the error measures are different, as we discussed, and so on. But coming then to the idea of saying we have this unknown target distribution, which we said was initially a target function, creating somehow the data we don't know, basically what this ideal function would be, but we know something was creating this data. And we say it is a target distribution because we said some of the machine learning problems are really the same X and different Ys out. Think about Netflix, you look at a video now or a movie now, and you give it a different rating in 2 years from now, and then you basically have a problem because it's not anymore a function. So hence, this is something that generated the data that we take as an assumption. And then we know already our X, this is our data set. Basically, that's the constants in learning. If you want, that's where we learn. And there's a certain probability distribution. Also, that we don't know, but we can assume from that, of course, when you have movies in Netflix, it's very hard to learn then suddenly the iris flowers or so, and iris setosa and iris virginica. It's not the same probability distribution, it's not the same data. So this is something which, of course, is then different. So continuing with the Chicago example, we said, okay, now we have this nice labeled training examples. We also found out there's like 2 things we want to do. Firstly, we have to pick from a hypothesis set of all possible machine learning tools we have. Let's say our tool set as machine learners. What do you want to have? A support vector machine? Do you want to have an artificial neural network with several hidden layers? Or do we say maybe the linear learning model in logistic regression, linear in weights, sum up the initial values that come up linearly and then using weights and so on, and then put it to some function, which is then in our case a logistic function. But the details you have seen in the last lecture, just wanted to say that, of course, the hypothesis set is loaded. So you can pick one out of very many, which is this G fellow here, out of the large hypothesis set. And this does not mean necessarily just if it is an SVM, ANN, or something. It is also relating to the parameters. Basically, you have set for these different models, right? So this is a 5 hidden layer, 2 hidden layer, 3 hidden layer, all different hypotheses. So we pick one, G, and this one, G, is of course the one that we hope approximates F, this kind of target function, almost as much as possible, right? Machine learning is never 100%, as we also learned by now. So there's always noise, there's always something in the data which prevents us basically from doing it in 100% style and learning from data. But still, it gives you an essence of learning from data, because otherwise you would have nothing potentially. So the other key ingredients were a learning algorithm. And in machine learning, many of these learning algorithms are fueled with optimization techniques. Here you have the stochastic gradient descent as one of the optimizers, if you want, doing it iteratively on this data set, on this training examples, however, right? So the test set will be left behind still. And then we're solving this iteratively, this kind of gradient descent technique, using then also the logistic function. And we have a so-called function or logistic loss, which gives you the guided label here and the input vector X. You basically have the learned weights. And you can always check if this actually example is now basically giving rise to the samples. Hence, it makes it supervised, right? We have the signal saying it's pass or fail. And if not, of course, we always will update the weights until a certain perspective, going, down the error slope, using the learning road, taking the derivative, and then from this, know exactly how far we go with the optimization. So this is, of course, a technique which should be filling a whole university lecture normally, maybe. And there are new optimizers like the Adam optimizer, for instance, or so, or Nestrelov momentum, that takes also the way how far you, or basically how quick you go downhill here. But this all captures the essence of saying that there's an optimization to solve, and the error surface, which is here just 2-dimensional in a way, very easy. This is something which, of course, can be also 3-dimensional and multi-dimensional, giving all the parameters. However, to knock down the error, we iteratively solve this with a learning algorithm. So we have a hypothesis set, which comes often with a, basically suggested learning algorithm. You would say support vector machines, quadratic programming. You have the artificial neural networks here. They usually go with backpropagation or backpropagation to time. There's many different approaches, but at least you have a learning algorithm that sort of fit the hypothesis set, but you need a yardstick. That's how I call the error measure, right? So the error measure is, as we said here, the logistic loss, saying, are you on track? Do you bog down or basically get nailed down the error and decrease it over time to somehow get to the final hypothesis at some point in time? And this is, of course, then captures the essence of machine learning. And to not spend too much time on the repeating elements, in basically the idea of doing it in a practical lecture was also we have these pipelines. We were not throwing data at the algorithms. We're using basically raw data that we then transformed into features in a very dense feature vector, if you remember, with a tokenizer and then this hashing idea. So we had a logistic regression model from training. And once this model is there, so from the training set, you know now what possibly new entities would be failing or passing. We have to put it to a test. And that's where now the evaluation comes in. If G really approximates F quite well, right? We call that out of sample data, right? So now we take the test set. As I was saying to you, this is what we throw in the corner in the beginning. Now it's a time for evaluation. We take it out and then basically have the same idea of a transformation. Hence the pipeline becomes very handy because now we see it on unseen data. But we of course want to transform the data the same way we did for training here. But now we do it for the test set. And then we will basically see that, of course, the logistic regression model is already there. So we don't need to really do this all again and have just a tokenizer hashing function and then perform, or let's say, in other words, do just inference on the logistic regression model. Hence, this is the way how, let's say, many of the machine learning algorithms work today. There are still a couple of them, of course, which change a little bit, particularly if you go to unsupervised learning techniques. If you go to reinforcement learning techniques, they're a little bit different. But still, here in the supervised setup, I hope you understand a little bit the game. And we did this also in a cloud, in a HD Insight using the Azure environment. But we also learned that this is basically done in AWS in a similar fashion and also Google Proc in a similar fashion. Now, today, it's about a conceptual lecture, more understanding virtualization data center design before we go actually again in practical topics. So hence the idea is to give you also assignment 2 very early. This will be related on MapReduce, deep learning, and so on. Still, it's important to understand a little bit the scalability, how it is enabled with data center designs, and why virtualization is such a big thing in it. Hence, our first part will really have a, let's say, very quick introduction to virtualization with a particular look on cloud computing technologies. It's a big topic. Virtualization could fill easily many different lectures. And it does in distributed systems, in operating systems. It has relationships to all these topics. And it's not only dedicated to cloud computing, but we will make it basically case for it, of really starting a little bit with basics. What is a virtual machine? What is an appliance? What is an image? And so on. And then, of course, we have some examples from the HD Insight Cloud again that were not really obvious to you, because if you create an HD Insight cluster, you're already high up the stack. We actually create Apache Spark. We wanted to have some virtualized worker nodes, virtualized head nodes, zookeeper nodes, as we have seen in the last lecture. So in a way, this is just using the underlying technique that you see here today of enabling, this whole cluster you have seen before. So this is something which usually you can do, particularly in the cloud, if you need a virtual machine, for instance, yourself with a certain operating system. But for the large operations in cloud computing, let's say creating a Kafka cluster, creating a Hadoop cluster, Spark cluster, as we have seen, this is somewhat underneath the radar because you just use virtualized servers even more or less without really knowing. And then the second part will do much more on the cloud data center design at large. So we have a certain term called economics of scale. That's something to understand also when you basically put it in context of cost. There's also a certain idea of data centers are so huge these days, and there are certain features that the failure can be assumed every single second or every single minute while operating, right? So how do you do resilience? How do you control or let's say, more notably, deal with the system failures that will happen now every minute. CPU overheated, another rack not visible or not reachable by the network, etc., etc. So we'll talk about this in the second part. And of course, here today in Iceland, and that's why there's a new thing, we wanted to show a little bit also what's happening in terms of green energy when we talk about building data centers, in terms of networking, infrastructure, storage, and compute. So this is something which we injected a little bit more. So we have a look on Icelandic data centers, what they have to offer, but also carefully review what are now this data center metrics that make it really scalable. This is scalability term is so important in the cloud. You have seen that by now a little bit when I was alluding to the scale down, scale up. In other words, basically shrink the cloud or basically increase the cloud, where also the term of clouds in a way comes from, right? So having some adaptability, dynamic behavior to really scale with the workload of the users is a key concern. And then already one student touched upon a question we had very early in the course. So why I want to do my private cloud, right? So when there's a public cloud like AWS, MS Azure, or Google, what on earth drives me to use OpenStack, for instance, to do a private cloud? And in a way, combining them means a hybrid cloud, what we will see today. So there's certain issues why you maybe don't want to rely on a complete public cloud and this still does some business on your own center. With this, we also fulfill lots of different promises from different lectures, as you see, lecture 1 most notably, but also lecture 3 had some idea of thinking about what happens if several users want to have an Apache cloud, and maybe use Spark in parallel. So many of them. So what happens if you have a multi-user cloud environment? So let us start a little bit this virtualization. So as the name suggests here of the part, it was really enabling the clouds to happen. We had this computation on data grids in the past, fueled by HPC and HTC. And this was really a topic coming up subtly, where the physical properties of a HPC system, is it very well interconnected, or is it maybe loosely coupled like the servers here in HTC? It basically gave another view on it, because virtualization was enabling us suddenly to have a virtual layer to logical and physical hardware. Logical in this sense means then what you really can use, but in the end, of course, there should be some physical hardware, but you basically just deal with the logical. And this means that maybe several logical, hardware virtualized resources can share one physical one. And with this lead to very different advances. And basically then in a way, if you want, really created the internet clouds that we see today. And you see many of the big vendors. I give you an example here, of course, just to say that, of course, Amazon gives you also an article that I would encourage you to look at. What is virtualization? So they describe it, why virtualization is also for Amazon a very key concern. Not talking about scalability in the first place. Without virtualization, there would be probably no data centers, would be not the scale up for multi-users, multi-tenant environments. And this would be then not maybe cost effective. So there are good points in looking at this. And of course, you can imagine that MS Azure and Google Proc have similar elements. And of course, as do many of the data centers we will allude today, that are going beyond the public cloud providers, the big ones we have always in the course. So review a little bit the virtualization concepts. I think now in class I would ask you, so are you, who of you knows the virtualization? I think many of you have this in the basics of computer science a little bit. And then I know some courses like distributed systems from my colleagues also touch upon virtualization. So I just do here a sort of a very quick introduction to come then to data center design later. However, the design itself of virtualization is not really new. It dates back quite a long time. And you see here a little bit, a traditional computer can be your laptop. You have some hardware, some memory, disks, whatever. And of course, a CPU. And then you would have your Linux, or you have maybe Windows installed. It doesn't really matter in this graphic. And then they run an application, right? And you run different applications. They all share the same host operating system. And it's an environment where you basically take all the resources there, you occupy them with different applications maybe, but it's still a sort of, one application oriented or one user oriented environment. And when you insert now this virtualization layer, which in some respect is called a hypervisor, for instance, then after virtualization, you have still this hardware, but you have a sort of virtual representation of all these hardware resources and share them with different, let's say, virtual machines. That's where the name virtual machine comes from, while this would be physical machines, right? And the virtual machines still enable you, of course, to leverage the physical machines, but they would have, for instance, maybe another guest operating systems for each of the different virtual machines. Hence, with the hypervisor, it enables you a little bit to think about if you not run Linux and Windows in parallel, for instance, right? And there are even solutions on your desktop computer. You can use VMware, there are solutions for your desktop and so on. Things where you can virtualize your computer and in a way also have a co-installation of Linux and Windows if you really want. And this enables now, of course, later on in the scale of clouds, much of interesting nice things, being really application-oriented, user-oriented, what the user wants. While basically in the left setup, you're sort of very fixed to the host operating system, let's say a Mac, and you can just install applications which are fitted to Mac systems, for instance. Hence, we insert here sort of layers that you see here a little bit, where the hardware is and where the operating system works in a normal physical machine, and then the application is on top, making use of the operating systems and hardware, a very traditional design to use really physical machines. However, if you now think about a VM in the sense of saying here, for instance, native VM means we, instead of installing an operating system, we have this sort of hypervisor technology to enable these virtual machines, and we have a sort of guest operating system and guest application on top of it that then can run, let's say, as a non-privileged mode in a way as a user of leveraging then functionality from the hypervisor equally as you would do from the operating system, right? And then make leverage or make use of the hardware resources, which then, of course, should be much more privileged because this is already in the operating system or in the hypervisor, let's say, environment. So this is something where making use of these technologies with this virtual machine manager, which then gives you an interesting grip on the hardware still being virtualized, you have the possibility to now inject different, let's say, models, how you would use that, right? While you here on the left-hand side are quite fixed, right? You have an operating system application. The hypervisor enables you now many different things, and hence there are different virtualization techniques that you can actually employ virtualization with. And they have different names, bringing us closer to the virtualization layer that should be also really bring to the highlight. It's basically the real hardware that you have, and it will always exist. The hardware, no matter how much you virtualize, at the end, of course, you want to have some real resources underneath, right? And this is an important part. And the virtual machine management, or this layer that you have in virtualization, is able to manage all of these resources, to share these resources with different virtualized environments. And this is basically, sort of speaking, it acts as an operating system of sorts. So because it's on the same layer as you see here, it offers you different access to hardware, locking it for some user and so on. If you think about storage, if you think about disk, maybe reading something, but still it's a very different element of really enabling then different operations in terms of guests, operating systems, and application that you see here in the graphic. So there are different components, though, to make this happening. And the virtual machine manager is now one that, of course, is important. And there are very different vendors providing those. Also, let's say, different capability. Some of them are doing virtualization. Some are doing host-based virtualization. Some have a full virtualization. And we will talk about this in a minute. But this is, of course, something where that the idea of the VMs now would be, and that's why you would employ it, to really enhance utilization of the service. So basically here, if the physical machine is not used, it's your application, it's basically idle all the time. The VM setup here enables you to run just different guests, let's say many different of them, all on the same hardware that helps mostly in the view of data centers to say, well, at least, one user's not using it, but many other using the hardware, reaching up maybe to a point where 99% of the hardware is always used by different users. Hence, the idea of the virtual machine is not only enhance the utilization of your own laptop, of your own, basically applications that you have maybe in smaller systems. It will be the key ingredient also what you think about larger data centers. But the basis and the fundamentals are really in this VMM design, have an abstraction layer, and then shared with different, guests. Hence, there are different operations also where we're interested in. Not you only as a user from a small application perspective, also if you run a big data center point of view, right? So this is something where several words and operations come in that we should talk about. And one of them is here, for instance, that you have hardware and storage is basically fixed, and they have a virtual machine learning manager on it and sort of multiplexed VMs on top of it. And this is something where, you see already one mode that on one hardware, if you want, there could be different applications with a different operating system on top. We call that multiplex VMs. And this is not just 2 users. This could be, of course, in a data center design, much, much more of these different users. Hence, it's important that you think about the scalability when I show this. Of course, I show the basics here in a virtual machine and virtual machine managers. But in the end, you would also have the possibility to also think about that we have with this much more options than having just one operating system dedicated to one hardware. Now, one other thing that is basically virtualization enabling is what you see on B, right? So we want to storage something. So to store something on certain storage, we call that suspension. That when you basically have the idea of thinking that we can do some, status of an application, we can easily cloud and storage this immediately. And with this, we have the possibility to suspend and then resume later. That's what you see in C, an application that was sort of running or a cluster that is prepared and used at a certain point in time. And some point in time will be not used, and you just drop that to storage. So all these images, these virtual machines that we will later explore, give you this interesting storing options that would otherwise not be really available. And this is another, let's say, very famous operation in clouds and also, of course, of virtualization as a whole. Now, think about errors and failures, as I said, beginning of the lecture, assume error in data centers all the time. It could be like the hardware is, let's say, error prone, it's overheated, there's some issue with the network, whatever it is, you see that in D, that some of the application is not really anymore running on this hardware. So hence, as a data center point of view, providing service level agreements, SLAs to customers, 99% availability, and so on and so on, you have to be prepared to perform a live migration. And that's what you see here, basically, of shifting then the application of the operating system just to another hardware to continue with the operation, having a hopefully very, very little downtime that is not really in the percentages a big footprint. And all of this is fueled by virtualization machine managers. So this VMM layer, this introduced virtualized layer, gives you exactly this and also scales quite significantly to cloud computing environments. So one example of this live migration example, you would say here that, it's another example of saying what's happening on one particular host A, and there's something, performed here, whatever application it is. You reserve the container on a target host, etc. You do basically copy paste and etc. etc. So the details are not important, but you basically do an application and suddenly there's something happening, right? So there's something not working, there's a downtime of some VM out of service. And then basically what you want to achieve with this live migration is now that you start already something in the background and say there's something misleading. So thinking about that we can maybe run something on a host B, right? And this was this live migration I had here. If you consider this as host A failing now with this error and then continue on host B. So there are techniques basically there that you see here, it's 165 milliseconds total downtime. So it's basically not even something which a user maybe necessarily noticed. And this is something where, of course, then the state from the virtual machine can be easily transferred to the other, let's say, host B, as we discussed. And with this, when the initial errors become more obvious, right, then this could be something where you can suspend then the VM on host A as it was host here, and redirect lots of elements to host B. And in the end, continue the operation with host B, having hopefully a very low downtime. And this affects the service level agreements that you would have in the cloud computing operations basically very much, and is also enabling us to work with different users at the same time. So then that means there are different ingredients, if you want, to a sort of virtual machine, and different terms that you should know a little bit. One of them is of a virtual appliance, so something which has already, let's say, an instant, and then we want to have different, terminologies clarified. And we will make the connection a little bit with the idea of doing this as MS Azure. You see that here on the right-hand side, for instance, if you do it in MS Azure, you can actually create a virtual machine. And in one respect, it has nothing to do now with the HD Insight cluster we created before, right, in 3.1. We now think purely about a virtual machine. We want to use it for some server, for something what we want to have running all the time. Could be my MP3 server, whatever, with all my different data that I don't want to share in the public cloud or whatever necessarily, in the sense of sharing it in a higher level service. I want to do my own thing in a virtual machine just on a file basis. Then there's something like you can expect around 80 euros per month, and then have a virtual machine on a very specific operating system. So you would be one of them here, right, in this angle, while many others will also use the same hardware you specify with another application and another operating system they will pick in MS Azure. And of course, then have access also to storage. Hence, there's physical resources, again, of course, underneath that are basically mapped, running various machine learning, various virtual appliances or virtual machines really during the run. And basically, you would say that running all together on an operating system, this would be this virtual appliance. And when now the live migration would really be necessary, then this virtual appliance can be easily ported to the other hardware platform, which of course means including all the different software libraries you have, like in our case, we have seen Apache Spark. That makes, of course, now the interesting thing of saying people can really leverage the hardware. So it's decreased costs. I don't need to do, for every different user, very different hardware. I share the hardware with many users, and also will use the hardware hopefully much more, and so on. So basically, in this words, we increase the efficiency of the hardware. And in having then the server consolidation aspect, it's also giving you the benefit again of live migration of other elements that makes the server really resilient and also available 99.9% basically towards an SLA or maybe of a cloud vendor. So virtual machines, virtual appliances is all very important. And one important distinction is now also between having really a running virtual machine instance and the image, which is now another interesting thing. So you would have an image prepared, and you see that a little bit like it is here. There's images prepared for certain operating systems that you can reuse again and again and again to instantiate different virtual machines in different states, right? So the image is basically very powerful, as it is suggesting here. It has an application system or an operating system, but also an application system of sorts, of maybe having different libraries, different elements already in the image that you can just reuse again and again and again. In previous times, it was quite actually also notable to have these images already prepared with many machine learning libraries, or with PyTorch, TensorFlow libraries for deep learning. So hence, this is something where cloud computing provider uses extremely a lot to have this pre-installed images. And you see that here, the recommended images that you basically can have different Windows operating systems, Red Hats, Ubuntu's, and so on. But in some higher level service, you can even combine this with application data. This is pre-installed images. For instance, let's say a deep learning appliance to really perform artificial intelligence. So you would have existing catalogs to do this. And just to basically summarize this a little bit with a view again on some examples, I want to come to some examples of virtualization now, but in a way that should be rather the content of a real virtualization, let's say course part, or at least basics in computer science. There are different areas, how the architecture works, full virtualization, para, virtualization, hypervisor, etc. And we have different examples we will just move through here a little bit. So when we look about Zen, for instance, you see here, it's an open source hypervisor. Hypervisor means you have this virtual area that we discussed to abstract from the real hardware to the, let's say, different areas of applications, which are different domains. And you see that the Zen enables you then also, as we discussed earlier, to have a Zen in Linux, a Zen Windows, in other words, a guest operating system working here where all your different applications work in. And that is the role of a hypervisor in a way that also then has to do, let's say, the contact to how you contact the hardware, right? So this is something which alludes to something of the device drivers that you need to have for hardware, and which is an important part also to consider that this needs to be done for the guest domains, for the applications through the operating system, which is sort of fake because it's virtualized, right? So it has not completely control. It always has to go via the hypervisor, except here in this example, we have this domain 0, which is a very special thing in Zen. So this was a hypervisor example, and you can go on full virtualization, for instance, also for VMware workstations, which is now a very, let's say, small scale example you can imagine from VMware. For your desktop, for instance, you would have still the host computer, you have your virtualized layer, and then the guest operating system that you basically have like a Linux or Windows of sort, and then your different user applications that normally have to go through the guest OS to do then basically the host computer and the system software access, reading a disk, and so on. And some of them are having then a shortcut of the user applications. And with this, you have sort of an idea of still have full virtualization, right, of the architecture through a hypervisor and so on. While in contrast to host-based virtualization, for instance, you will see that instead of having this hypervisor, which is now doing everything on top, you would have still a host operating system we call the host-based virtualization architecture. Let's say some of you will know they're running perhaps, for instance, a Linux host operating system, and then can actually have as a virtualized layer, then a virtual machine of some sort inside it, and then actually have a Windows inside Linux running. That is working, right? Or have, of course, directly applications, but this host-based virtualization architecture is also, of course, something that you can use to combine and give different access to different, let's say, operating systems. It's a different view of different perspectives. Also, when you think again that in the end, they all want to access your hardware, this virtualization software, and the host operating system would be fully capable of doing it, of course, but still the hypervisor had have some special function enabling maybe more performance. Not the whole host operating system is carried, which maybe is not necessarily if lots of load. Then you have this para virtualization example, KVM, some of you know it. It's also very simple that you have this interesting para virtualized guest OS. So you still count a lot on the virtualization layer, but have lots of benefits in a way of having, you know, the para virtualized operating system that is in a way there to enable then the access again through the hardware, through the virtualization layer, but could be also in some of the areas a little bit like, you know, kind of high cost to do. So it depends how you really learn KVM. It's just an example here of another sort of idea that you don't introduce necessarily a fake hardware or virtualized hardware for all the different you know, applications, for all the different virtualization elements, but rather share this real hardware with some different specific calls that you can then execute. So you see lots of that has introduced, of course, into an area what you would say operating systems deal with hardware resources, and virtualization has to do the same things in order to make the virtualized layer happening. So in one respect, there are certain overlap with operating systems and also this idea of how to run virtualization. Hence, we show you this as a, let's say, small stimulating example what virtualization is. But what is now cloud computing? If you think about it, provide virtualized resources from an internet cloud. We had this before, this graphic saying there's this big bubble here, this big cloud. There's lots of hardware storage, which is can be expanded, can be shrinked, can be changed over time with different resources. And this is really where you pay in the cloud for a lot in order to get your requests satisfied. And this is all fueled by virtualization, right? Hence, our part 2 of the lecture will talk about this much, much more than the introduction of virtualization in the first part here. Just to give you a sneak preview, when you think about that you have this idea of virtualized resources and data centers. So there's still the hardware that is there. But of course, then you very quickly come in a very large data center to the idea of a virtualized layer. What are now really the resources you have? And then you have this different virtual machines we were alluding to enable some specific, virtualized infrastructure that you pick, like HD Insight, for instance, right? Which was more or less on this level and thinking about different elements already on a virtualized infrastructure. And then you have different services on it. Different users can use it, like you in your assignment. You will be getting to a resource group that then have access to use this virtualized infrastructure. And in the end, the hardware platform, but you will never have the grip really to the hardware platform, right? You all use this virtualized layer on top of it. And this is all, as the example now concludes on virtualization on a larger scale, the key ingredients to cloud computing, also to make it multi-user, multi-tenant, that basically you have the possibility to shrink up and down to the needs, to enable flexible resource sharing, as we would call this, with different many users. So a little bit let out from 10,000 feet perspective would look like this. There's one large physical infrastructure maybe, but there's resource sharing going on with many different users using all the Spark HD Insight. And some of them are maybe using the same HD Insight given security constraints, but then also some others install their own HD Insight. The point is now the virtualization enables you to create these different clusters among the cloud, right? With concrete, really resources, which are short of here, in a way showing you that there is a sort of fake cloud, right? Which you can use. But of course, the cloud would have limits in the end still. Even if you think about you can shrink up and down, in the end, the data centers will have limited resources. But as the data centers also work together, have a different grid together, this is another point of saying, well, they have ability to different orders of scale, but then also performing live migration, maybe to another center, to get resources also together of another center. And with this basically can mimic the idea that the resources are completely infinite. You see this a little bit here also, coming back a little bit to the idea of physical versus virtual, that you have here another data center design of where to put the workload now from the different ideas into a virtualized data center, which probably looks more like this. You have different VMs, some of them using a database, some a web server, some hosting, again, a database, some do middleware. But you have the load of different VMs during the runtime of the cluster, and they add up to different applications. But of course, it's a Lego blocks here a little bit suggest, if you want, right? Lego in a sense of it's completely different to each of the application. You do some load balancing, you have to do and schedule this into your different ideas of the, let's say, physical cluster. Hence, you can also see that there are certain technology trends. Of course, some want still a multi-core CPU, very cutting-edge performance, while others want to have a many-core GPU for running some AI workloads. So this is something where lots of the future trends and the current challenges, and this is, of course, to satisfy the needs also for heterogeneous requirements and workloads. And that's what, of course, the cloud vendors do. And they significantly use, as you see with different applications here, with database, web server, middleware, also then the idea of thinking about more different services to different users. And middleware can stand also here, for instance, for the Apache Spark cluster that we're going to use, in the assignment or we have used. Hence, we need solutions which are bigger, server virtualization software, or even bigger cloud data infrastructures, virtualization techniques. And one of them is the VMware ESXi server. I give you as an example. It has the same principles, of course, as a VM kernel, abstracting from the, let's say, physical resources you have, the network interconnect, disk, memory, or CPUs, GPUs. And then you have the virtual machine, this kind of virtualization layer introduced, working then of virtualized resources with different guest OS. It just basically optimized for really cloud infrastructure. You can read about this a bit more on VMware here on this one. And there are different solutions for different problems. You see vSphere is also very similar than the one we have seen there. And also it offers a vCenter suite, where you basically also have for data center all you need. And the interesting thing is basically many of these elements are sort of based on what we also will learn later with the cloud operating system and OpenStack, right? So this is technology that enables you then quite a flexibility what you really want to provide in the overall cloud. And you see the VM sphere is a little bit bigger than just the different services or infrastructure services we learned before from virtualization. Gives you also monitoring and different elements and control over this, basically all data center that you run in your company. Hence, the vCenter suite is unifying this all and then providing to your elements in the company different, let's say, application domains. Hence, a different options really how you do virtualization in a data center. This video shows again the basics a little bit, so I would encourage you to look at before we dive in lecture 2 today. So we break here for 10 minutes and see you then.